Do you find topics related to financial assets, financial leases, and amortized cost hard? What about notes receivable or notes payable? How about bonds? How about the trial and error? Or the loans receivables and payables? Or the employee benefits? How about the effective interest method? Or net present value? Or profitability index? Or the internal rate of return? And other accounting topics related to time value of money? If you found those hard, then the reason might be it's because you did not understand these red colored topics. Most of the students tend to just memorize formulas on these topics instead of understanding its concepts. But don't worry, this video will help you understand the totality of the time value of money and apply what you have learned in the illustrative problems provided. And in just less than 2 hours, the knowledge of a whole subject which is normally taught for months will be yours. Now, let's get started. Welcome again to my channel. Today, we will be talking about time value of money. Actually, this is just the part 1 on my discussion on the time value of money. My series of videos will be centered on 3 main topics. The first is the mastery of future value, the second, the present value, and the interpolation. We're going to tackle not just the concepts but also the calculations. This particular video is mainly discussing the topic future value, but it also includes other topics. Well, here's the list of the subtopics. Number 1, concept of time value of money and simple interest. Number 2 is the concept of compound financial interest and the future value. Number 3 is all about future value of 1. Number 4 is future value ordinary annuity. Number 5 is future value annuity due. And the bonus topic, which talks about multiple and equal investments. It is important to note that these topics includes illustrations and solutions. So this is again Gletzmar Igcasama, and let's start. So we are now on the first part entitled Time Value of Money and Simple Interest. So what is time value of money? The concept of the time value of money is that your 1 peso today will be worth more in the future because of interest. Actually, the simple interest is directly related to this one. So if you have a debt or an investment, those will grow because of interest. For example, you want to invest 1 million to earn 5%. How much will it be after 2 years and 6 months? To answer that, we need to get the future value of the investment, which is the principal plus interest. The principal in this case is the amount invested. The interest is computed as principal times rate times time. But I would like to emphasize that whenever you are given a rate just like this one, the 5%, please assume that it is an annual rate unless otherwise specified. So let's compute first the interest. The interest is 1 million, which is the principal, times the rate of 5% times time. So this time can also be expressed in fraction, where the numerator can be the number of months over 12 months or the number of days over 360 or 365 days. So again, 1 million times 0.05 times 2.5 years is 125,000. So in order to get the future value of the investment, we need to add the principal of 1 million plus the interest of 125,000. We have 1,125,000. So that's it for part 1. So we are now on the second part and the third part, which is entitled Compound Interest, Future Value, and Future Value of 1. So to start this, we need to compare first the simple interest versus the compound interest. So interest is considered simple when it is charged only to the principal. So how about compound interest? The compound interest is an interest not only charged to the principal but also on the interest accrued but still unpaid or uncollected yet. It might be clearer if we have an illustration. This illustration is coming from the previous example where you want to invest 1 million at a rate of 5%. The question is the same, which is how much will be your investment after 2 years and 6 months. However, there is a red colored text here which states that the interest is compounded semi-annually, which basically means the charging of interest is every 6 months. So applying the concept of compounding, we have a timeline for 5 periods. Why are we considering 5 periods, sir? It is because of this compounding mentioned in the problem. So now, each period that we have is only for 6 months, and each year has 2 periods. So 2 periods times 2.5 years, that is equivalent to 2 years and 6 months, the 2.5 years. So we have 5 periods. So let's go now to the computation. So you have 1 million now, and after 6 months, it will grow to 1025. Actually, the 1 million has been multiplied by 1.025 or 102.5%, where 100% is for the principal invested and 2.5% is the interest. So where did the 2.5% come from? It is from the 5%. But then again, this 5% pertains to annual rate, and we are just considering 6 months, so we're gonna use the 2.5%. So beware on the compounding schedules mentioned in the problem because it will affect the computation. So in the succeeding years, it will follow the same pattern. The 1,025,000 will be multiplied by 1.025 and it will become 1,050,625. But if we analyze this, the whole 1025 in this period, which is composed of the principal of 1 million and the interest of 25,000, has been subjected or has been charged with interest because, as you can see, the totality of this one has been multiplied by 1.025, in which this 1.025 is equivalent to 102.5%, which is already inclusive of interest. So that's the concept of compound interest. Let me remind you again that the compound interest is the interest charged not only on the principal but also on the unpaid or uncollected interest. So let's continue the timeline until we get the final answer. So the 1,050,625 times 1.025, you're gonna get 1,076,890.62. You multiply that again by 1.025, you're gonna get at the end of year 2 1,103,813, and on the last period or at the end of 2.5 years or 2 years and 6 months, your investment will be 1,131,408. Let's go now to the future value of 1. When answering the question how much will be the value of the investment after a specified period of time, just like this one, you can answer it with a timeline just like this one. But if we are talking about long periods of time, let's say for example, instead of 2.5 years, we're gonna consider the 25 years, then it would be difficult to get the answer through timeline. Because if that's the case, you're going to consider 50 periods. So if this is the case, we can use the future value of 1. What is this? This is simply the formula 1 plus I raised to the power of positive n, where I is the interest rate per period and n is the number of periods. So what will you do with this future value factor? You are just going to multiply it with the investment and then you're gonna get the future value of the investment. Or stated differently, in order to get the future value of the investment, investment times 1 plus I raised to the power of positive n, or future value of 1. So let's try it with the recent problem. We have 1 million times 1 plus 0.05 raised to the power of 5. You solve first the future value of 1. Then you should be getting 1.131408 and so on, because this has been rounded off. Then multiply it with the investment and then you're gonna get 1,131,408. As you have noticed, they have similar answer with the timeline method. So if you know the future value of 1, then it doesn't matter how many years is the maturity date for investments or debt, you can solve it easily. That is why this time value is sometimes called as the long cut and this one is the shortcut. So that's it for part 2 and part 3. The part 4 and part 5 is all about future value ordinary annuity and annuity due. So it will be better if we go directly to the illustration. So the problem is very much similar with the previous. However, instead of investing 1 million at one time, you decided to invest it in staggered basis of 200,000 every 6 months. So what will happen? On a timeline analysis, you will start investing at the end of 6 months. So if this is now, you're not going to invest here. You're gonna invest here, the 200,000, and then the 200,000 will grow times 1.025. It will become 205,000 at the end of year 1. So after that, you're going to invest the second 200,000, and then at the end of year 1, you have 405,000. The 405,000 will then grow again times 1.025. You have 415,125 plus the third 200,000 that you're gonna invest. You have 615,125. You multiply that again by 1.025. You're gonna get 630,503. The fourth investment of 200,000 will be added, and then you're gonna get 835,03. And lastly, in the last or the end of 2.5 years, the 835,03 times 1.025 will have 851,266 plus your last investment of 200,000, then you're gonna get 1,051,266. But then, if we are talking about long maturity periods again, it would be unwise to make a timeline analysis like this one. So we have the shortcut or the formula, which starts with the base formula. As we discussed earlier, that's 1 plus I raised to the power of positive n. But this time, you're gonna add 2 elements, which is the minus 1 and the divided by I. So that is what do we call as future value of 1 ordinary annuity. And what are we going to do with this future value factor? Of course, you multiply that with the investment per period. So let's have the proof. Let's substitute the elements of this formula with the given in the problem. So your investment is 200,000 times 1 plus 0.025 raised to the power of 5 minus 1 over 0.025. Now, if you solve this one, and if you're correct, you should be getting the 5.256328 and so on. And you're gonna multiply this one with 200,000. So your investment will become 1,051,266 at the end of 2.5 years using the shortcut or the formula. Now, the 1,051,266 is the same with the timeline analysis. How about the annuity due? So let's assume the problem above, except that the 200,000 is made at every beginning of the period. So now you're going to invest the 200,000, and then it will grow to 205,000, and then you add the second investment of 200,000. You have 405,000, and it will grow to 415,125. Plus 200,000, you have 615,125 times 1.025, you will have 635,03 plus 200,000, you have 835,03, and then your last investment will happen at the end of year 2, but the 835,03 will grow to 851,266 plus your last investment, you will have 1,051,266. But then again, the question is after 2.5 years, so 1,051,266 will have the opportunity to grow, and it will grow up to 1,077,547. So these two are similar because you have 200,000 here as investment 5 times. However, they are different on the timing. The first investment here is due immediately. That's why the fifth investment happened at the end of year 2. How about here? The investment only started after 6 months. That's why the fifth investment of 200,000 happened at the end of 2.5 years. In the shortcut or the formula, you have investment per period times the base 1 plus I raised to the power of n. However, as you remembered, we added two elements for the ordinary annuity, the minus 1 and the over I. And since we are already here, we need to add two other elements, which is the plus 1 on the n and the final minus 1. So this is what do we call as future value of 1 annuity due. Now, to guide you, since the formula has been complicated already, so let's substitute the given in this formula. So you have 200,000 times 1 plus 0.025 raised to the power of 6. So as you can see, in the previous we used 5, but since we are already on the annuity due, you added 1, so that's why it's 6. So before you solve any others, you need to solve first the 1 plus 0.025 raised to the power of 6 before you deduct this one. Now, if you got the answer for this one, that's the time that you are going to deduct the 1. And then after you get the answer for this one, that's the time that you are going to divide the 0.025. And after you get the answer for this whole, that's the time that you are going to deduct the final one. So, if you did that, you'll be able to get the 5.387736 and so on times the 200,000. You're going to get the same answer with what is your answer on the timeline analysis. So that's it for future value of 1, ordinary annuity, and annuity due. Let's have a little summary. So if the question is how much will be my investment after a period of time, then if that is only one-time investment, then you use investment times 1 plus I raised to the power of positive n, or what do we call as future value of 1. But if your investments are multiple uniform investments and it is contributed at the end of each year or each period, then you're gonna use investment per period times 1 plus I raised to the power of n. However, you're going to add two things. The first one is minus 1 over the I. And if it's still multiple uniform investments, however, it is contributed at the beginning of each period, then you use the investment per period times 1 plus I raised to the power of n minus 1 over I, but you're going to add another 2. You have plus 1 on the n and the final minus 1. So that's it for part 4 and part 5. Let's go now to the final topic, which is entitled Multiple and Equal Investments, and let's go directly to the illustration. You want to invest 400,000 at the end of year 1, but only 300,000 at the end of year 2 and 200,000 at the end of year 3. The investment is to earn 7%. How much will it be after 4 years? So let's prepare a timeline for 4 years. In this particular problem, 4 years is equivalent also to 4 periods since there is no mention about quarterly, semi-annually, and etc. So now, at the end of year 1, you're gonna have to make an investment to 400,000, and then it will grow to 428,000, and then the second investment will be added. You will have 728,000 times 1.07. You're going to have 778,960 plus your last investment of 200,000. Then you will have 978,960. But since the question is how much will it be after 4 years, the 978,960 will be multiplied by 1.07. Then you're gonna have 1,047,487. How about the shortcut or the formula, sir? Unfortunately, there is no shortcut. Each of your investment payment, 400, 300, and 200, will be treated separately. So the formula is investment times 1 plus I raised to the power of n in order to get the future value. So let's start with the recent one. The recent or the latest payment that you're going to make is 200,000. It will be multiplied with 1 plus 0.07 raised to the power of positive 1, which will equal to 214,000. But we need to explain why is the n positive 1, sir? Because this 200,000, your last payment, has only 1 year of opportunity to grow. The next is 300,000 times 1 plus 0.07 raised to the power of positive 2, why 2? Because it has 2 years to grow. So you will have 343,470. And of course, the last is 400,000, and you are going to multiply it with 1 plus 0.07 raised to the power of positive 3 because it has 3 years of opportunity to grow, and then you'll have 490,017. If you're going to add these 3, you're gonna get the same answer with what is on the time value. So that's it for all the parts. So we have already answered one particular question in this video, and that is how much will be the future value of the investment, where the rate and the amount of investment was given. In the next video, we are going to answer 2 questions. The first question is, if one wanted a specific value in the future and the rate of return is given, how much should one invest? For example, Mr. A wants to have 3 million in 3 years time to buy a car. If the rate of return is 10%, how much should A invest now or invest per period? Meaning, the desired future value is given, the 3 million. The rate of return is also given. What's missing is the investment or investment per period amount. The second question is, if one has available money to invest, how much should be the rate of investment to have a specific amount in the future? For example, Mr. A wants to have 3 million in 3 years to buy a car. Mr. A can invest 230,000 per quarter. What should be the rate of return of investment in order to reach the targeted 3 million after 3 years? So in the second question, the rate is the one missing. The investment amount is present, as well as the desired future value is given. To get the missing rate, we need to discuss interpolation on the next video. So that's it for this particular video. You are welcome to play and replay this video until you are satisfied. If this helped, click like, subscribe, and share to other accounting students, and also please hit the notification bell to be updated on my next videos. Today, our topic will be the time value of money, specifically the future value. In order to master the future value, you need to answer these 3 important questions. Number 1, what will be the future value of an investment if one will invest this much now or every period at a specified growth rate? So in here, the amount of money to be invested and the growth rate are given. You are to find out the investment value in the future. The number 2 question is, how much should one invest now or per period if one wanted this much in a specified period and specified rate? So here, the desired future value of money and the interest rate is given. What's missing is the amount to be invested. In number 3, how much is the interest rate should the present investment grow to get the desired future value of the investment? In simple terms, the amount available for investment and the desired future value of the investment is given. You just need to find the interest rate so that your present investment will really reach the desired future value. The question number 1 has already been answered in video number 1. The link is in the description below. Check it out first before you continue with this video, and for those who have already seen the video number 1, let's answer question number 2 and question number 3 right now. Let's try to answer the second question by an illustrative problem. But before we go to that, I would like to highlight something that we have learned from the last video. These are some formulas to get the different future value factors. If we are to have one-time investment, we are gonna use 1 plus I raised to the power of n. And then, if we have multiple uniform investments at the end of each period, we're gonna use the 1 plus I raised to the power of n pa din. However, we're going to add 2 elements, which are the minus 1 and the over I. But if we are going to have multiple uniform investments at the beginning of each period, we're going to follow this one. However, we are going to add another 2 elements, which are the plus 1 on the n and as well as the final minus 1. But let me remind you again that please see video number 1 first to fully understand this video lecture. The link again is on the description below. So that's it for the highlights from the past video. Let's go now to the illustrative problem. Mr. A wants to have 3 million in 3 years because he wanted to buy a car. The interest rate is 10% per annum. How much will he invest? So there are two cases here. So in the first case, we are to assume that Mr. A is to invest one time big time immediately today. So we can have a timeline analysis for 3 years. So after 3 years, we have the desired future value of 3 million. We also know of the 10% rate because it's given. In the past video, we start right here in the beginning and then we multiply the amount of our investment at 1 plus interest rate. In this case, we have 10%. So we have 1.10. Why 1.10, sir? Again, the 100% investment is represented by 1 here, and then we add the interest rate, that's why it's 1.10. In this particular case, since we are going to start here, the opposite of what we've learned in the past, so instead of multiplying, we are going to divide 3 million by 1.10, and we're gonna get 2727,272.72. This amount will then be again divided by 1.10 and we're gonna get 2479,338.84, and lastly, we are going to divide it with the last 1.10, that gives 2253,944.40. That means, if you want to have 3 million after 3 years time, and you wanted to invest at one time, big time, immediately today, you should invest this amount, 2253,944.40. We can also have the shortcut or formula, which is investment times 1 plus I raised to the power of n equals the future value of the investment. We used 1 plus I raised to the power of positive n because there is only a one-time investment mentioned in this case, number 1. So let's substitute. The investment is missing, right? But the interest rate is given, so we can get the future value factor from 1.10 raised to the power of positive 3. And since the desired future value is given, the 3 million, then there is only one unknown. To get that, we have to simplify the equation first by getting the 1.10 raised to the power of 3, and we have 1.331. So in order to get the unknown, you just have to divide the 3 million with 1.331, and then you're gonna get the amount of investment, which is very the same with what is our solution on the timeline analysis. To master the topic, let's have the case number 2 and assume he will invest every beginning of the year starting immediately. So let's go to the timeline analysis. Of course, you're gonna invest 3 times. One here, another one here, and another one right here. And after 3 years, we still want to have 3 million pesos because we want to buy a car. Now, we are still going to use the 1.10 because the rate of return is unchanged. So in order to get the answer, divide 3 million with 1.10. So we have 2,727,272.72. And we cannot go back further because we don't know the amount of this one, and this one. So in cases like this or problems like this, the timeline analysis cannot be able to get the answer. So what do we do? Of course, we use the shortcut or the formula, which is investment times 1 plus I raised to the power of n. But since it talks about multiple investments, you have minus 1 and over I. And since, according to the case, the investment is every beginning of the year or every beginning of the period, we need to add other 2 elements. We have plus 1 on the n and the final minus 1. So investment times this one equals the future value. So let's substitute. So the investment is unknown, but we can get the future value factor by getting 1.10 raised to the power of positive 4 minus 1 over 0.10, and we have the final minus 1 equals the desired future value of 3 million. So investment, if you're going to summarize this one, times 3.641 equals 3 million. And then if you want to get the unknown investment, you just have to divide 3 million by 3.641, and you're going to get the investment is equivalent to 823,949.46. So let's check if ever your investments of 823,949.46 will really become 3 million at the end of 3 years. So let's have your first investment right here, the second investment will be here, and the third investment will be right here. So let's start. 823,949.46 times 1.10, you're gonna get 906,344.41 plus 823,949.46, you're gonna get 1730,293.87. You multiply that again by 1.10, you're gonna get 1903,323.26 plus 823,949.46. Then you'll have 2,727,272.72. And lastly, you multiply it with another 1.10, that gives 3 million really. So that's the proof. So meaning, if Mr. A wants to have 3 million after 3 years and he plans to invest every beginning of each year, then his investment should be 823,949.46. So, what if the specified rate is absent, or you're gonna find the rate? That is up next. We are now on the last part of our video lecture, which is focused on answering the question, how much is the interest rate should the present investment grow to get the desired future value of the investment? In order to understand this, let's jump to the illustration. So we have Mr. A wants to have 3 million in 3 years to buy a car. So all of the problems in this video lecture are quite similar. So A can invest 230,000 per quarter. What should be the rate of return of the investment in order to reach the targeted 3 million after 3 years? Let us have the timeline analysis. However, let me tell you in advance that the missing rate can't be found using the timeline. But we are still going to have the timeline to illustrate the pattern of your investments. Like for example, in year 1, you're going to contribute 230,000 at the end of quarter 1, as well as at the end of quarter 2, quarter 3, and quarter 4. The same pattern will be used by the year 2, and of course, at year 3. However, at the end of the third year, we should be having 3 million. We are expecting to have 3 million as the value of the investment. So aside from this pattern, we are going to use this timeline analysis to check our answer later. The important question is, how do we get the missing rate? So to get the missing rate, we need to do two things. The first one is the trial and error, and the second one is the interpolation. So first, I'll explain the trial and error. This particular step has two requirements. So requirement A is to get the appropriate formula in getting the future value factor. We have three choices as discussed earlier, but since our problem is a case where there are multiple uniform investments of 230,000 at the end of each quarter or each period, then we use 1 plus I raised to the power of positive n minus 1 over I. And the second requirement is to set the objective, which is in this case is to know the rate for the investment to reach 3 million after 3 years. After those requirements are set, the trial and error will follow. For example, we want to try 10% per annum. So we have to use that in the appropriate formula mentioned under requirement A. So we have 1.025 raised to the power of positive 12 minus 1 over 0.025. Sir, why is it 1.025? It was supposed to be 1.10 because the interest rate is 10%. Guys, the problem stated quarterly, right? So we're gonna use 10% per annum divided by 4 quarters, which is 2.5%. That is why we used 1.025. And before you ask again, the N is actually 3 years times 4 quarters, so we have 12 periods. So I hope that's clear. If we summarize this, then we're going to get 13.79555.3, and you multiply that with the quarterly investments of 230,000, then you are going to get 3,172,977, which resulted a little bit higher than what we are aiming for, which is 3 million. So let's try a rate that is lower than 10% so that we can have an answer lower than 3,172,977. So let's try another. Let's say, for example, we have 5%. So remember that we are not going to use the 5%. We need to divide the 5% with 4 quarters so that we can get the quarterly rate. So if we are going to apply that one, we have 1.25%. So 1.0125 raised to the power of positive 12 minus 1 divided by 0.0125. So we will have 12.8603361. You multiply that again with the quarterly investments of 230,000, then you are going to get 2,957,883, which is slightly lower than the 3 million that we are aiming for. So that's the end of the trial and error. Actually, you can try as many times as you like, but for the trial and error to end, remember to pick the two rates which will result nearest to the desired future value, which is in this case the 3 million. So just like these two tried rates. And number 2, you need to remember that it is much better for one of the trial rates to result in a slightly higher amount than what we are aiming for, just like this one, and the other trial rate should result in a slightly lower value than the desired future value, just like this one. So that's all for trial and error. Let's go to step 2, the interpolation. So the first step is to organize the rates and the resulting figures. What do you mean, sir? So a while ago, we tried 10% and 5%. So you put it right here, and on the opposite side the resulting values. So when we tried 10%, it resulted to 3172977, right? And when we tried 5%, we got 2957883. Next is you need to put the 3 million in the middle, as well as the x representing the unknown rate. And then we find x. The question is, how do we do that? Focus on the tried rates. So we have 10% and the 5%, and then get their difference, which is 5%. So if we express that in an equation, it means to arrive at the second tried rate, you're going to deduct 5% from the first tried rate. So you need that equation because if you wanted to find the effective rate, you will follow the same, which is 10% minus 5. However, the 5 will still be multiplied with a fraction. The question is, how do we get the fraction? In the value section, the first minus the second value, the difference in absolute values, absolute value meaning we don't care if it is positive or negative, will become the numerator. So in this case, we have 3,172,977 minus 3 million. So we have 172,977, the numerator, while the denominator is the first value minus the third value, which is 215,094. So simplifying the equation, 5% times this fraction, you are going to get 4.02. So we have 10 minus 4.02, then we're going to have an effective rate of 5.98% or 6% per annum. And if you wanted to convert it, you have 1.5% per quarter. Sir, what if we choose other trial rates? Like for example, instead of using the 10% and the 5%, we are going to use 8% and 4% here. So will we arrive at the similar answer? Of course, if you follow the steps. So you can try it if you want to. Sir, we want proof. Okay, let's check if the 1.5% per quarter is really correct by using the timeline analysis that we have prepared a while ago. And if it is correct, then after 3 years, the value of the investment should become 3 million or near 3 million. So let's start. Let's multiply our investment with 1.015, applying the 1.5% per quarter. So 230,000 times 1.015, you're gonna get 233,450 plus 230,000. So that's 463,450. And then this 463,450 times 1.015 again, then you're gonna get 470,401.75 plus 230,000, you have 700,401.75 times 1.015, you're gonna get 710 plus 230,000, that's 940,907.78. So that's on the first year. On the year 2, the 940,907.78, that's the end of year 1, will become the beginning of the year 2 times 1.015, you're gonna get 955,021.39 plus 230,000, that's 1,185,021.39 times 1.015, 1,202,796.71 plus 230,000, we have 1,432,796.71, and then again multiply it with 1.015, we have 1.54 plus 230,000, we have 1,684,288.66. you continue multiplying, and then you're gonna get at the end of the second year 1,939,553. On the year 3, we have 1,939,553 from the year end of year 2 times 1.015, you're gonna get 1,968,646.30 plus 230,000, and then we're gonna get 2,198,646.30 times 1.015, we have 2,231,626 plus 230,000, we have 2,461,626 times 1.015 plus 230,000, we're gonna get 2,728,550.39. And lastly, times 1.015, we're gonna get 2,769,478.64 plus 230,000, that is 2,999,478.64. The value is slightly off, I know, but that is because of rounding of factors. So 299,478.64 has a difference with the 3 million. But if you want to be strict, then interpolate again and come up with trial rates which will result to nearest to 3 million. For example, this 10%, you can change this into 6%, and instead of putting 3172977, so you're gonna put here the 299,478. And instead of using 5%, for example, you can change this to 6.10%. It's really up to you, but follow the steps, of course. So that's it. We are now on the last installment of the time value of money topic. In this video lecture today, we are going to answer 4 questions only. The question number 1 is how to get the present value of the receivable or payable. Receivable if you are the creditor and payable if you are the debtor. In here, we have 3 sub-questions to answer. And the sub-question A is, what is the present value of my liability or receivable if I or someone is required to pay a single sum of money in the future? To understand that, let's jump directly to the illustrative problem. Example, you promise to pay someone 3 million after 4 years through a non-interest bearing note. The implicit rate is 12% compounded annually. What is this non-interest bearing note? For starters, note is the shortcut for a written promissory note where the debtor promises to pay an amount in the specific future date. So what is the meaning of non-interest bearing, sir? Well, a regular debt agreement is normally composed of terms for principal payments and interest payments of the debtor, right? So if non-interest bearing, then there is no agreement as to the interest payments. So if you are the debtor, it's as if you are just going to pay only the principal. But the truth is, even if there is no interest agreement, it doesn't mean that there is no interest charge. The interest is already included in the payments. In this case, it's already included in the 3 million. So that interest is what do we call as implicit interest. That is why As you can see in this problem, there is an implicit rate of 12% mentioned. So again, this 3 million right here is not only composed of principal payments, but it also includes interest. So let's analyze. Is your payable 3 million now? Really? Right now? Of course not. It is 3 million after 4 years. Actually, this amount already includes interest for 4 years. So we need to remove the interest for 4 years first in order to get the amount of your payable or debt now. So the process of removing such interest is technically known as discounting process. So how do we do that? So we can have the timeline analysis. So today is here, and then after 4 years you're gonna pay 3 million, and then you will be debt free. And in the problem we have 12%, so we have to use 1.12 in our working back or computation. So we can work back. So if it is 0 here after paying the 3 million, then that means your debt is 3 million here before the payment. And then let's work back. So we're going to divide 3 million with 1.12 instead of multiplying because we are working back. So 3 million divided by 1.12, you will have 2,678,571. Divided by 1.12, we have 2,391,582. Another divide 1.12, 2,135,341. And the last, divide it by 1.12, and you're gonna get 1,906,554. So your liability is only 1,906,554. It became 3 million because the 3 million includes interest. Of course, there is a shortcut, which is payments times 1 plus interest raised to the power of negative n or negative number of periods. So let's substitute. The payments is 3 million and then 1 plus 0.12 raised to the power of negative 4. So to summarize, we have 3 million times 0.635518,078, which is the summary of this 1.12 raised to the power of negative 4, or the answer. So 3 million times this one, you will have 1,906,554, which is the same with what is the result in our timeline analysis. And by the way, this 1 plus I raised to the power of negative n is what do we call as present value of 1. Sub question B is, what is the present value of my liability or receivable if someone is to pay multiple times at the end of each period? So it is the same with sub question letter A. However, you will be required to pay multiple times. For example, you promise to pay someone 750,000 every end of the year for 4 years through a non-interest bearing note. The implicit rate is 12% compounded annually. So in timeline analysis, you are gonna pay here 750,000, and then here also, as well as here, so that your liability will become 0. And according to the problem, the implicit rate is 12% compounded annually, so we are still going to use the 1.12. Now we can work back. If this is 0 after 750,000 was paid, then this is also 750,000 divided by 1.12, then you're gonna get 669,643. But before the 750,000 was paid, it is 1419643, and then divided by 1.12, you will have 1267538 plus 750,000, you will have 2,017,538. You divide that again with 1.12, then you're gonna get 1,801,374 plus 750,000. We have 2,551,374. And lastly, you divide it with the last 1.12, then you're gonna get 2,278,012. So your debt today is 2,278,012. And then we have the formula-based solution, which is payments times 1 plus I raised to the power of negative n. However, we're going to add two other elements, this 1 minus and the over interest. This formula is what do we call also the present value ordinary annuity. Again, payments times present value of the ordinary annuity, which is this formula, is the present value. It's now time to substitute. So the payments is 750,000 times 1 minus 1.12 raised to the power of negative 4 over 0.12. So if we are going to summarize this one, we're gonna get 3.0373493, and then multiply that again with the payments of 750,000, then we are going to get 2,278,012, which is the same with this one. The last sub-question is the same with the previous illustration. However, the 750,000 will be paid at the beginning of each period. So in timeline, it looks like this one. So if you observe, the last payment of 750,000 happened in the end of the third year instead of at the end of the fourth year, because in substance, the end of the third year is also equivalent to the beginning of the fourth year. Of course, we are still to use the 1.12, so we can start working back. So here is 0 plus 750,000, you will have 750,000 divided by 1.12, you will have 669,643, plus 750,000, you will have 1419643 divided by 1.12, you're gonna get 1267538, plus 750,000, you have 2,017,538 divided by 1.12, we have 1801374, plus 750,000, you have 2551374. We can also get this 2551374 by multiplying payments with 1 minus 1 plus I raised to the power of negative n over I. The same with this one. However, we are going to add two elements. One of it is the plus 1 here in the negative n and the final plus 1. So let's substitute. We have 1 minus 1.12 raised to the power of negative 3 instead of negative 4 because of this plus 1 over 0.12 plus 1. And then you multiply that with the payments of 750,000. So if we're going to summarize this one, then you're gonna get the present value factor of 3.4018313 and multiply that again with the 750,000, and then you're gonna get 2551373. There is 1 peso difference. It is because of rounding off factors. And by the way, this formula is what do we call technically as annuity in advance or present value annuity in advance. In some other authors, it's called the annuity due. Before we go to the summary of this slide, I have a bonus knowledge for you. So for example, what if you wanted to get this 2391582 or this 1267538 using the formula approach, not using the timeline analysis? Can you do that? Yes, of course. You just use the formula. These formulas. However, you need to revise the n. So in here, if you wanted to get the 1906, you use negative 4, right? But since you wanted to get this one, then you're going to revise this n. It will become 2. Because from the maturity date, you need only to go back 2 years because you want to get the 2391582. The same with this one. If you wanted to have the 1267538, again, you revise the negative 4 into negative 2. Now, let's have the summary. So, to get the present value of your receivable or liability, or to answer the first question, then if it involves one-time payment only, you use payments times 1 plus I raised to the power of negative n. This formula is what do we call as present value of 1. And if it involves multiple uniform payments at the end of each period, then you use payments times present value of 1 ordinary annuity, which is 1 plus I raised to the power of negative n. However, there are two additional elements, the 1 minus and the over I. But if it involves multiple uniform payments at the beginning of each period, then use payments times present value annuity due or annuity in advance, which is the same with this one. However, there are another two additional elements, the plus 1 in the negative n and the final plus 1. So that's it for question number 1. Question number 2 is coming right up. We are now on the second question, which is how to get the payment amount. To be specific, let's assume in here that the present value of your debt is given, as well as the interest rate or the implicit interest rate is given, as well as the terms like the maturity date or the payment dates and etc. are also given. What's missing is the specific payment amount. That's what's missing. To understand it further, let's go directly to the illustration. The proceeds you receive from a financial institution today is 2,470,000. The interest rate is 12%. You are to pay an amount every end of 6 months for 2.5 years. How much will you pay semi-annually to settle the debt? So to analyze this, we can use a timeline. However, let me be clear that this timeline cannot find the amount that we are looking for. So we are only going to use this timeline for two purposes. One is to understand the problem further, and number two, later, we're going to use this for checking purposes. So in here, based on the problem, you are going to recognize the present value of liability of 2,470,000, and you should remember that the proceeds that you have received is actually the present value of your liability today. And then according to the problem, you're gonna pay here, 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 and here, and also here, so that you will have a zero liability at the end of 2.5 years. It is also mentioned on the problem that the implicit interest rate is 12%. However, we cannot use the 12% because it said in the problem we are having semi-annual payments. So what are we going to use? We have 6% or 12% divided by 2. So we're gonna use 1.06. So if we're going to simplify the problem, it's as if it's telling you if your liability is 2,470 and it will grow at 6% every 6 months, how much will you pay so that your liability will be fully satisfied at the end of 2.5 years? Again, we can't get the answer using the timeline, so we are going to use the formulas. But first, let's go back to the formulas that we've learned a while ago. So we have three formulas. So if one-time payment, we're going to use payments times 1 plus I raised to the power of negative n. But if the problem is dealing with multiple uniform payments at the end of each period, that would be payments times 1 plus I raised to the power negative n. However, there is 1 minus here and over interest. But if we're going to deal with multiple uniform payments at the beginning of each period, we're gonna use payments times 1 minus 1 plus I raised to the power of negative n over I. But in this one, we have plus 1 on the negative n and the final plus 1. And since the problem is clearly multiple uniform payments at the end of each period, then we're going to use this number 2. So payments times 1 minus 1 plus I raised to the power of negative n over I equals the present value of the debt. And then we substitute. So in the problem, the payments is not given, but we can get the amounts for the present value factor. So we have 1 minus 1.06 raised to the power of negative 5 divided by 0.06 equals the present value of 2,470, which is given in the problem. So if we're going to summarize this, then we're going to have 4.21236,378, and then we have 2,470. So in order to get the payments, you just have to divide the 2,470 with 4.21236,378, and the payments is 586,369. Let's check if our answer is correct. So we have to put the payments here and here and here and here and of course here, and let's see if our liability will be 0 after 2.5 years. So let's start. 2,470,000 times 1.06, you have 2,618,200. However, you're gonna pay the first 586,369, then you will only have 203,1831 times 1.06. We have 2,153,741 minus 586,369. We have 1,567,372 times 1.06 minus the third payment. Then we have 1,075,045 pesos times 1.06. We have 113,951 548 minus 586,369, then we have 553,179. And lastly, we have 553,179 times 1.06 equals 586,369.74 minus 586,369. Supposedly, there's an answer here of 0.74. However, the difference of 0.74 is just due to rounding of factors. So we have proven already that 586,369 is the right answer. But let's analyze further. I told you earlier that payments for non-interest bearing notes includes principal and interest payments. So we need to prove that now. So as you can see here, we have the beginning liability of 2,470,000. However, after 6 months, it became 203,1831. So it's safe to conclude that there is a principal payment of how much? 438,169. That is the difference between these two balances. How about the interest, sir? Since we have the total payment of 586,369 and the principal payment is 438,169, the difference of the two, which is 148,200, is the interest payment for a total of 586,369. However, there is another method of getting the interest payment. And how do we do that? Remember, the beginning liability is 2,470. However, after 6 months, it was multiplied by 1.06 and it became 2,618,200. Actually, the difference between that two is the interest payment. So, in short, if you wanted to get the principal payment, you get the difference between the beginning balance of the liability and the ending balance, and the interest payment is just the difference of this one and this one. So let's complete the analysis for all of the periods. So we have the difference of this one is the principal payment of 464,459, and the interest is this one minus this one. We have 121,910, and of course that is still 586,369 all in all. On the third, we have the difference of this one is the principal payment, and the difference of this and this is the interest, for a total again of 586,369. The same with here, you're gonna deduct 1075045 minus 553,179. So that is the principal payment, the difference of 521,866, and the interest is just 113,948 minus 1075045. We have 64,503. Still, it is a total of 586,369 payments. And the last is 553,179 minus 0. You have a principal payment of 553,179, and the interest is the difference between these two. So 33,190.74 for a total of 586,369.74. And let me remind you again that this difference of 0.74 is due to rounding of factors. So that's it for question number 2. Question number 3 is coming right next. Question number 3. The third question is how to get the effective rate if it's not given. To be specific, please assume that the present value of your debt is given, as well as the terms like the payment dates or the maturity term or the maturity dates is given, as well as the specific payment amounts is given. What's missing is the interest rate, just like this problem. The proceeds you receive from a financial institution today is 2.2 million. The interest rate is unknown. You are to pay an amount of 500,000 every end of 6 months for 2.5 years. How much will you pay semi-annually to settle the debt? To understand the given situation, let us explain it using the timeline. So, at the very beginning, you are to record 2.2 million as your liability, which is equivalent to the proceeds that you have received from the financial institution. And according to the problem, you are gonna pay 500,000 each of the 6 months period. Then, if you're going to add this 500,000, all in all, you're gonna pay 2.5 million. So based on our analysis, it is very clear that there is an interest charge because you're gonna pay 2.5 million, however, you have only received 2.2 million. The question here is, how much is the interest rate? However, we cannot use this timeline in order to get that missing rate. If you can remember, if the rate is missing, we need to undergo trial and error as well as interpolation. To find the unknown rate, we have step 1 trial and error as well as step 2 interpolation. In the last video, we already did the trial and error and interpolation, but in the context of the future value. The steps that we did there, however, are also the steps that we are going to do here in the present value, which starts with the trial and error. But before we do that, we need to fill up 2 requirements, right? So the first one is getting the appropriate formula. Again, we have 3 options, but we are to use 1 minus 1 plus I raised to the power of negative n over I. It is because based on the illustration, it is clear that you are to have multiple uniform payments at the end of each period. Please remember this. If the problem is silent, you assume that the multiple payments are made at the end of the period. The second requirement is the setting of objective. So our objective here is to find the rate that will be applied on the appropriate formula so that the payments, which is 500,000 times the appropriate formula, will result to a present value of 2.2 million. So that's our objective. And since we have already the 2 requirements, the appropriate formula and the objective, we are now ready for the trial and error. Let's say, for example, we're gonna try 10%. However, we cannot use the 10%. Why? Because the illustrative problem mentions semi-annual periods. So what rate are we going to use? Of course, 10% divided by 2. So applying, that would be 500,000 times 1 minus 1.05 raised to the power of negative 5 over 0.05. So to simplify, you have 500,000 and we simplify this, you're gonna have 4.32947,667. 500,000 times this one equals 2164738. But since it's lower than our 2.2 million goal and we need to increase this one, so we have to try a lower rate, let's say 8%. Sir, why do we have to try a lower rate? In the past, when we are doing this in the future value context, you said if you wanted to make the future value higher, you try a higher rate. Well guys, that is only true for the future value. Here in the present value, always remember that the interest rate and the present value has an inverse relationship. So in summary, when we talk about future value, the rule is the higher the interest rate, the higher the future value of your investment. But when we talk about present value, the higher the interest rate, the lower the present value of your payables or receivables. Sir, we need the logic behind the inverse relationship of present value and the interest rate. Okay guys, so let's compare and contrast. For example, situation 1, you receive from your loan application 2.2 million, but you are to pay 2.5 million just like this problem. However, we have situation number 2 in which you only receive 2 million but you are still to pay 2.5. Of course, we can conclude that in these 2 situations there are interest charges because you're gonna pay more than what you have received. However, which interest charge is greater? Of course, the interest charge in situation 2 is greater because you receive lesser proceeds. So let me emphasize it again. The higher the interest rate, the lower the resulting present value is. So I hope it's clear now. Let's go back to the problem. And again, we need a bigger present value than 2,164,738 because our goal is 2.2 million. So let's try 8% as I've mentioned a while ago. But we are not going to use the 8%. We're gonna use the 8% divided by 2 semi-annual periods or 4%. So let's substitute. We have 500,000 times 1 minus 1.04 raised to the power negative 5 over 0.04. To simplify that, we have 500,000 times 4.451822331, and then we're gonna get 2,225,911, and that is our trial and error. But let me remind you again that you can have lots and lots of trials, but the trial and error ends when you have tried 2 rates which will result near to the desired value. So our desired value is 2.2 million. These 2 rates resulted nearer to the desired value. and one of the tried rates resulted to a slightly higher value than the desired, which is this one, and the other one resulted to a value lower than the desired present value, which is this one. So that's it for our trial and error. We're now prepared for the interpolation. In this particular step, the first thing that we should do is to arrange the tried rates as well as the resulting present values. So we have 10%, and the 10% resulted to 2,164,738. We also tried 8%, and the resulting present value is 2,225,911. After that, we're going to put in the middle the 2.2 million, which is the desired present value, and the X, which represents the unknown effective rate. The next thing that we should do after the arrangement is to have an equation which highlights the difference between the 10% and the 8%, the first and the second tried rate, which is 10%, the difference is 2% in order to get the second tried rate of 8%. So why do we do this? Because if we're going to get the effective rate, we're going to use this, particularly the 10 minus 2. So we have effective rate is equivalent to 10 minus 2. However, the 2 will be multiplied with a fraction first. And that fraction is, the numerator is the first and the second amount, which is 2164738 minus 2.2 million. Supposedly, the answer is negative. However, we are interested with the positive values or the absolute value. So we have positive 35,262. And the denominator is the first minus the third. So we have 61,173. So in order to simplify that, the effective rate is 10% minus 1.15, or the effective rate is 8.85% per annum, or effective rate is 4.42% per semester or per semi-annual period. Let's check if our 4.42% per sem is correct, and let's apply the 1.0442 in our timeline before. So we have 2.2 times 1.0442, you have 2,297,240 minus your first payment, then you're gonna have a liability of 1,797,240. Now you multiply that again with 1.0442, that gives 1,876,678 minus 500,000, we have 1,376,678 times 1.0442 again, then you are gonna have 1,437,527 minus 500,000, that is 937,527 times 1.0442 again, then you're gonna have 978,966 minus your fourth payment, we have 478,966 times 1.0442, you will have 500,136. This is supposed to be 500,000, but because of our rounding off factors, that's why there's a discrepancy of 136. So this is supposed to be 0. But if you wanted to have the exact rate, then you repeat the trial and error and interpolation. But this time, you need to choose two rates which will result closest to 2.2 million. So that's it for question number 3. The last and the fourth question is, what if we're talking about interest-bearing debts or receivables? Let's go directly to the problem to understand this. So you were granted a loan for 2 million. The interest rate is 10%. You are to pay the principal in 5 years, but you will also pay the interest every year. So actually in here, you have to think that you have two types of debts, the principal and the interest. So if the problem is this simple, then we need not compute the present value of your liability because it's directly 2 million. So what will happen? Let's have the timeline. So here, you're gonna recognize 2 million as the present value of your debt. And then you multiply that with 1.10. It's because according to the problem, the interest rate is 10% and you're gonna get 2.2 million. However, you're gonna pay interest every year. So that is 10% times 2 million. So we have 200,000. And then you're back to 2 million. Actually, on the second year to fifth year, the cycle will continue. Times 1.10 and then 2.2 minus 200,000, 2 million again, until you are going to pay at the end of the fifth year the principal of 2 million. Sir, we want proof that the present value is really 2 million. Okay, then we can use a formula-based solution to prove that. As I have told you earlier, you have two types of debts here. You have the principal and you also have the interest. And since the principal is to be paid only once, which is after 5 years, it would be appropriate that we're going to multiply it with 1 plus I raised to the power of negative n. On the other hand, the interest is to be paid multiple times at the end of each period, so you need to use 1 minus 1 plus I raised to the power of negative n over I. Now let's substitute. So you're gonna pay principal of 2 million after 5 years, and you multiply that with 1.10 raised to the power of negative 5. If you're going to summarize this, then you're gonna get 0.6209213. So this one times this one, you're gonna get 1,241,843 rounded to the nearest whole number. And then as to the interest, you're gonna pay 200,000, the 10% from the 2 million. This is the agreed interest rate times the agreed principal. Sometimes this interest rate is also called the nominal interest rate. So you multiply that with 1 minus 1.10 raised to the power of negative 5 divided by 0.10. And if you're going to summarize this, you're gonna have 3.7907868. So 200,000 times this one, you will have 758,157. So you add them up, the sum is 2 million. So that's the proof that the present value is really 2 million. Things will only get complicated with interest-bearing notes or debts when the agreed principal is not the same with the proceeds received by the debtor. Let's say, for example, we have situation number 2. Let's assume the last problem where you are to pay 2 million principal at the end of 5 years and interest of 200,000 every year. Except that you only receive 1,855,809 from the creditor as proceeds. This usually happens when the creditor charges or deducts something like direct origination costs or service charges or transaction costs and the like. Sometimes, these charges are abused by the creditors. The debtors are usually misled to believe that the interest rate charge is small, but in reality, there are a lot of hidden advance deductions. Anyways, let's go back to the problem and analyze this situation. It is very clear that the interest rate charge here in this situation number 2 is not 10% only. It is higher. Because you are not just required to pay for 10% interest, the creditor also deducted something from your supposed to be proceeds of 2 million. The question is, what is that effective rate? Surely it's not 10% because if it is, then according to these calculations, you should have received 2 million as proceeds. However, you can find that through again trial and error and interpolation, which if you remember, we'll start with getting of the appropriate formula. The only difference is that the appropriate formula will be for 2 payments already. One is for the principal and the other one is for the interest payments. Luckily, we already have that. These are those formulas. So after getting the appropriate formula, let's find the objective or let's set the objective. And that is, what is the rate that if we are going to substitute that rate with these formulas will result to the present value of 1,855,809. Next is we will have the trial and error. To make this fast, let's use the 10% because luckily we have already computed and it resulted to 2 million. But in order to get a lower value, because we're trying to find the rate that will result to 1,855,809, we are going to use a much higher rate, say for example 14%. But before we do that, I'll say this again to remind you that the rate and the present value has an inverse relationship. So if you want to decrease the present value, then increase the rate, just like in this case. Now, let's substitute the 14% in the appropriate formulas. So we have 2 million times 1.14 raised to the power of negative 5. If you're going to summarize this, you're gonna get 0.51936,866. So this one times this one, you are going to have 1,038,737. And then you have the interest of 200,000 times 1 minus 1.14 raised to the power of negative 5 divided by 0.14. So we have 3.43308,097 times 200,000, then the answer is 686,616. The sum of these two is 1,725,353. So that's it for trial and error. Let's go now to interpolation. But first, you arrange the tried rates 10% and 14% here, and then on the opposite side, the resulting present value. So 10% resulted to 2 million and 14% resulted to 1,725,353. Then put in the middle the desired present value of 1,855,809 and x representing the unknown rate. And then you need to make an equation that highlights the difference between the first tried rate of 10%. The difference is 4%, and then you're gonna get the second tried rate of 14%. Why? Because we're going to use this 10 plus 4 in getting the effective rate. But before we do that, the 4% will be multiplied to a fraction in which the numerator is the difference between this 2 million minus 1,855,809, which is 144,191. And then the denominator is the difference between this first 2 million minus the 1,725,353, resulting to 274,647. And then you summarize this. When you summarize that, you're gonna get 2.10. So meaning the effective rate is 10 plus 2.10 or 12.10% per annum. But if you're going to round off, you have 12% per annum. Of course, you wanted to check if ever that is correct. So let's have the timeline. And let's use the 1.12 because our answer is 12% per annum. So according to the problem, you have a present value of 1,855,809. And then, you're gonna pay after the end of 5 years a principal of 2 million and you're gonna pay interest of 200,000 each and every year. So, let's see if ever this 1,855,809 debt of yours will really become zero at the end of year 5. So, 1,855,809 times 1.12, you have 2,078,506 minus 200,000, you have 1,878,506 times 1.12, you have 2,103,927 minus 200,000, you have 1,903,927 times 1.12, you have 2,132,398 minus 200,000, you have 1,932,398 times 1.12 again, you have 2,164,286 minus 200,000, you have 1,964,286 times 1.12, then you are going to get 2.2 million. Minus the last interest payment, you have 2 million. And minus the principal payment, of course, it will become zero. That means the effective rate is really 12%. Sir, what if the 1,855,809 is missing, however the 12% effective rate is given? So what will happen? Of course guys, you will not need to have the interpolation and the trial and error because the effective rate is already there. What you need to do is to get the 1,855,809. And how do you do that? By using the 12% and applying it with the appropriate formulas right here. So meaning, instead of 2 million times 1.10, you're gonna have 2 million times 1.12 raised to the power of negative 5. And here, 200,000 times 1 minus 1.12 raised to the power of negative 5 to get that 1,855,809. Sir, one last thing. This 200,000 is 10% out of 2 million, right? So, the effective rate is already 12%. Do we need to revise the 200,000? No. 200,000 stays as it is. Why? Because you cannot change the fact that you are going to pay 200,000 interest every year as per agreement with the creditor. I hope that's clear. So, that's the end of this video lecture. So if you have questions, please comment that below and I'll try to answer as soon as possible. If it helped, then please click like, subscribe, and share this to those who need this. Please also hit the notification bell to be updated on my next videos.